Swayam Prabha. Digital India. Educated India.
So in this option D, there is a acetyl methyl group, so that generally appears between 2 to 2.2 ppm. So we can rule out, since the given problem has a peak at 3.8, which is a singlet for 3 hydrogen atom, we can completely rule out the option D. Then we are left with other 3 options only. Let us rule out which one cannot be done. So if you look at the coupling constant values for the aromatic ring, the J ortho coupling is around 6 to 9 Hertz, and J meta is around 2 to 3 Hertz, and J para is around 0 to 1 Hertz. So based on that, we can say what is the relationship between the 2 hydrogen atoms. We can easily find out. So for C, if you look at the option C, here we have H1, H2 and H3. 3 hydrogen atoms are there. Each one can have both ortho coupling and meta coupling, because this H1 will have ortho coupling with H2 and meta coupling with H3. And if you look at H2, H2 will have 2 ortho couplings, one with H1 and one with H3. And if you look at H3, the H3 has 1 ortho coupling with H2 and 1 meta coupling with H1. In other words, all the 3 hydrogens will appear as a doublet of doublet. But in the given problem, there is only 1 doublet of doublet is given. The other 2 hydrogens appear as a simple doublet. So we can rule out C also, because here the compound C does not have 1 doublet and 1 doublet of doublet and 2 doublet type hydrogen atoms. So we can completely rule out C. Then the next one is between A and B. So the tricky thing in the case of A and B is, if you look at A and B, there is 1 hydrogen atom which is in between 2 substituents. So H1 here is flanked between an amino group and the methoxy group, and the other 2 hydrogen atoms are basically, one is adjacent to a nitro group, another one is adjacent to a amino group. So in other words, we have 1 hydrogen which is flanked by 2 functional groups in option A. And if we come to option B, here again this H1 is flanked by 2 substituents, one by the nitro group, another one by the methoxy group. And here again the hydrogen atoms 2 and 3, both of them are adjacent to either nitro group or amino group. So that means 1 hydrogen is isolated, the other 2 hydrogens are adjacent. So this is the same combination present in A and B. Now we have to find out what is the given values will match with which one of the option, either A or B. So this is the little bit tricky one. And if we look at both the structures, H1 in the case of option A has a meta substituent at H2. H2 is having 1 ortho substituent and 1 meta substituent. H3 only has a ortho substituent. Similarly, if we go to B also, this also matches the same thing. So in other words, what we can say is the H1 will be split by H2 with a doublet, because this is only the meta coupling, and then H2 and H3 both will be appearing as a doublet of doublet, one by the ortho coupling and another by the meta one, and the H3 is split only by the ortho coupling. So these are all the ways by which these will actually come. And so in A, what we can say is H1 and H2 will be actually coming at the upfield with respect to 7.3, and in B, if we look at the amino group has only one hydrogen, that is H3, which is ortho to it. So that only will appear in the upfield region. So based on that, we can easily figure it out what is going to be the right structure. So this ruled out the structure A for the compound, because only in compound B or the option B, we have two hydrogen atoms which are appearing at the downfield region with respect to 7.3, which is the standard benzene hydrogen atom. So two hydrogens which are appearing in the downfield region is due to the electron withdrawing nature of the nitro group. So amino group donates electron, nitro groups withdraws electron. So because of the nitro group which is withdrawing the electrons, these two hydrogen atoms which are ortho to that appear in the downfield region, and this exactly matches with the given data. So what we can say is A is not the structure for the given NMR data, and B is the only thing that exactly matches with the given data, and we can say B is the right solution for this particular problem. Let us move on to the next problem. So in this one, an AX system gave 4 lines at delta 4.72, 4.6, 1.12 and 1.0 ppm away from the TMS using a NMR spectrometer operating at 100 megahertz, and what are the values of JAX in hertz and delta AX in ppm respectively? This question was asked in June 2013. 4 options are given. A is 12 and 3.6, B is 6 and 3.6, C is 12 and 2.86, D is 6 and 2.86. Let us work out the problem by a mathematical solution for this one. So here there are some equations we have to follow. The first one is, how do we calculate the coupling constant? The coupling constants are generally calculated by the difference in the frequency of the values of the hydrogen atoms which are coming in the NMR spectrum. That is, we are going to compare between delta 1 and delta 2, that is two different peaks which are coming at for each hydrogen atoms multiplied by the frequency of the NMR machine. So this actually gives the actual coupling constant for this one. So here we have the values 4.76 and 4.72 and 4.6 as one combination. Another one appears at 1.12 and 1.0. So if we find the difference between delta 4 minus delta 3 or delta 1 minus delta 2, so these two values if we calculate, they both are appear to be at 1.12, and when we 1.2, and when we multiply that by 100, we are going to get 12 hertz. So the difference between 4.72 and 4.6 is 0.12. So when we multiply the 0.12 by 100, that equivalent to 12 hertz. So that is how we actually get the value of the JAX. And if you are going to calculate the delta AX, the equation is given as the root of delta 1 minus delta 4 into delta 2 minus delta 3. So if we substitute the values, it comes to be root of 12.95, and that root when we take, square root when we take, that comes to 3.6 ppm. So the value 12 and 3.6 is the right answer. Let us move on to the next problem. So an organic compound having the molecular formula C10H14 exhibited 2 singlets in the 1H NMR spectrum and 3 signals in the carbon-13 NMR spectrum. The compound is, 4 options are given here. This question was asked in December 2013. So let us work out how to solve this problem. So here we are going to compare the singlets in the proton NMR spectrum and the carbon-13 signal. So these are all the 2 things we are going to compare. And let us start with the first one. In the first one, the compound is highly symmetrical. So these 2 hydrogen appear as a chemically equivalent hydrogen atoms, and we have a very extremely symmetrical structure. So these 2 methyl groups are also appear as a single chemically equivalent one. So we have only 2 types of signal, that is A and B are the two types of hydrogen signal that is possible for option A, and for option B we have A, B and C. Three different types of hydrogens are present in structure B, and in the structure C we have A, B, C. Three different types of hydrogens are present, and in D we again have A, B, C. So except the structure 1, all the other structures have three different type of hydrogen atoms, but the problem has given only two types of hydrogen atoms for the right compound. So we can say A is the right option for this particular problem. And if you look at the carbon values also, carbon signals also, for the first structure option A we have three signals, because there is a methyl group, there is a quaternary carbon, and there is a aromatic carbon, so a CH carbon. So these three, since the molecule is highly symmetrical, we only have three types of signals. And for compound B we actually have 7 types of carbon signals, and for option C we have 5 types of carbon 13 signals, and for option D we have 4 types of carbon 13 signals. So the first option only matches with the given problem. So the right option for this problem is option A. Let us move on to the next problem. Among the following, the correct statement of the following reaction is: there is a carbonyl compound given, this undergoes a Grignard reaction followed by treatment with the acid that leads to an alkene. So this is the reaction that is happening, and this question was asked in December 2013, and 4 different options are given. The first option says A is the major product and it will have 5 signals in the proton decoupled carbon 13 spectrum, and B, again A is a minor product, but the compound will have 8 signals. And option C is B is the major product that will have 5 signals in the carbon 13, proton decoupled carbon 13, and option D is B is the minor product having 5 signals in the proton decoupled carbon 13. So we are going to find out what is actually going to be the final product. So let us do the reaction. If we do the Grignard reaction, we are going to end up with a alcohol which undergoes dehydration to give the final product. So we have 2 types of product that is possible, because this hydroxy group can lose hydrogen atoms. So there are 2 options. One is this purple hydrogen can be lost, or the blue hydrogen can be lost. When the blue hydrogen is lost, we end up with the major product A, and when the purple hydrogen is lost, we end up with the minor product C. So based on the Seitzef rule, we can actually say the more substituted one will be the thermodynamically stable product. So that is the reason we call this as a major product. And in this compound, if you look at, since this is a major product, and how many carbon 13 decoupled C13 signals are possible is 8 in this particular case. And for the minor product B, we only have 5, because this molecule is basically a symmetrical molecule. So since it is symmetrical molecule, we only have less number of carbon 13 signals. So in that, the last option B is the minor product and it will have 5 signal is the right option for this particular problem. And let us move on to the next problem. The correct structure of the compound which shows following carbon 13 NMR depth 135 data is C13 depth 135, the negative peaks at the delta 30.2, 31.9, 61.8 and 114.7 ppm, and the positive peak at 130.4 ppm. This question was asked in June 2016. 4 options are given here. So now before solving the problem, we do need to know what is this depth 135 value. So when we talk about the depth 135 value, so this is nothing but distortion enhanced by polarization transfer, and these are generally done in pulses. So the different types of pulses which are given are 45 degree, 90 degree and 135 degree. So based on that, some of the CH2, CH and methyl carbons appear at different places, either positive peak or as a negative peak. So with respect to the 135 pulse, the negative peak means they are CH2, that is methylene carbons, and positive peak means they are either CH carbons or CH3 type carbons, and the quaternary carbons do not appear in the 135 degree pulse. So based on that, whatever is given here, we have 1, 2, 3, 4 types of negative peaks. That means there are 4 CH2 carbons are present in the given compound and 1 positive peak. That means either it is CH or CH3. So if you look at all the 4 structures, let us look at how each compound can give different types of peaks. So for A, there are 4 CH2 carbons and 1 CH carbon. We have 1, 2, 3, and 4. These are all the 4 CH2 type carbons, and there is 1 CH type carbon. So it will show 4 negative peak and 1 positive peak. And when we go to structure B, there are 1, 2 CH2 type carbons, and we have 1 CH, another CH, and CH3. So that means 3 types of either CH or CH3 type carbon. So total, if we calculate, there are 3 positive peaks. And when you go to structure C, there are 3 CH2s. We have 1, 2, and 3 CH2s, and we have 1 CH and 1 CH3. So that means it will show 2 positive peaks and 3 negative peaks. And when you go to structure D, there are 1, 2, 3 CH2 carbons are there, and 1 CH3 carbon is there. There is one more quaternary carbon. So the quaternary carbon will not be shown. So in other words, we have 3 negative peaks and 1 positive peak for the option D. So based on that, we can clearly say option A is the right one, which is having a 4 negative peaks and 1 positive peak. So this is the structure of the given compound. And let us move on to the next set of problems, that is based on IR spectra. So in this particular case, the IR spectrum of a para-nitrophenyl acetate compound is given. The carbonyl absorption band appears at 4 different options are given. This question was asked both in December 2012 and December 2013, but only the values are little bit different. Other than that, they are very close enough to one another. The structure of phenyl acetate is given, and the structure of para-nitrophenyl acetate is given, because para-nitrophenyl acetate can actually undergo resonance structures because nitro group is electron withdrawing. So this can actually form a nice resonance structure. So due to which the IR values will shift. And if you look at the correct answer is the highest frequency, which is given 1770. So that is the value for the IR frequency for para-nitro phenyl acetate. So this is the carbonyl absorption. Because of the resonance, we are getting this value at 1760 or 1770. Let us move on to the next workout problem. So here 2 columns are given, A and B. We are going to match the carbonyl stretching frequency set between column A and column B. This question was asked in December 2015. So there are 3 different kind of lactone type compounds are given. So lactones are basically cyclic esters. So we have no double bond in the compound option P, and in Q we have a double bond, and in R we have a alpha beta unsaturated system. And the column B has the IR frequency values which are given here. And now, before solving this problem, we do need to know the resonance structures. How do they influence the IR frequency? So in the case of the compound where there is a double bond, let us start from the base value where there is no double bond present in the cyclic system. So the base value approximately comes at 1770 as the standard thing. So here oxygen can donate its lone pair of electrons, and the resonance can happen towards the carbonyl oxygen. So we have a partial single bond character and a partial double bond character that exists. So the carbon oxygen bond most of the time tend to remain like either double bond or single bond because of the resonance contribution. So that's the reason this appears around 1770. Basically, when the single bond nature increases, obviously the frequency also generally reduces. So it has to, when the double bond nature is more, obviously the frequency is also going to be more. If it is having a single bond nature, then the frequencies are going to be shifted to the lower values. So this is with respect to the resonance of the carbonyl group. So in the case of the first structure as shown here, the oxygen's lone pair can partially go towards the carbon-oxygen double bond. Similarly, it can also go towards the carbon-carbon double bond. In other words, what we can say is 50% of the time it may be towards the CC double bond, 50% of the time it may be towards the CC CO double bond. In other words, the probability of the carbon-oxygen bond existing as a double bond is actually more in the case of structure 1. So the value of the IR frequency appears at 1800 per centimeters. If we go to the other extreme, which is the alpha beta unsaturated system, so in this particular case, there are two donors. One is the oxygen's lone pair, another one is the carbon-carbon double bond. Both can donate its electrons so that the carbon-oxygen double bond in the carbonyl group remains as a single bond most of the time, because there is plenty of electrons available for it, and oxygen being more electronegative tend to pull the electron towards itself. So the carbon-oxygen carbonyl bond tend to be like a C single bond O most of the time. So that is the reason, because of the higher conjugation, that C double bond O remains as a double bond. In other words, it is appearing at the 1750. It is appearing at a lower frequency and at 1750 per centimeter. So that way we can say what is going to be the relative values of these two things, and based on that we can say the option A is the one which is actually the right one. The double bond which is present in the cyclic system and which is isolated double bond which is not in conjugation with the carbonyl group appears at the higher frequency. A simple lactone appears at 1770 per centimeter, and the alpha beta unsaturated system appears at 1750. So with that we can easily figure it out, what is the role of conjugation in IR frequency. Let us move on to the next one. Here the major product X formed in the following reaction exhibited a strong absorption at 1765 per centimeter in the IR spectrum. The structure is given, the structure of X is, we are given 4 different options, A, B and C, D. This question was asked in June 2011. Now the reaction, what is happening is PCC. PCC is basically a mild oxidizing agent. So the mild oxidizing agent will oxidize the hydroxy group. So in the compound A, there is a carboxylic acid is given as the product, because PCC cannot oxidize a hydroxy group to a carboxylic acid. Since it is a mild one, it will only oxidize maximum to an aldehyde unit. So without looking at the IR spectrum or anything, we can simply rule out this carboxylic acid peak, because that is not going to be formed during this particular PCC oxidation. And we are now left with the 3 other options, B, C and D. And B is a dicarbonyl compound, but this actually had undergone cyclization. So this is also going to be quite difficult to cyclization by simple oxidation. So this also can be easily ruled out, because the diketone cannot be possible. And we are now left out with the 2 things. One is a ketoaldehyde, because there is a secondary alcohol, there is a primary alcohol, both can undergo oxidation. So in that case we end up with a ketoaldehyde, that is possible. So option C is one, and the next one is option D, which is a lactone. So we have to now find it out what is the right one. But if you look at carefully, in option C we have 2 carbonyl groups. That means we have to have 2 carbonyl absorption frequencies, but we are not having 2, we are only having 1. So in other words, we can also rule out C is also not the structure. So the option D is going to be the right structure. Now we have to only figure it out how we can actually get this particular structure in this particular reaction which matches with the given values. So as we discussed earlier, the carboxylic acid is ruled out based on reaction type, and also based on IR. If you want to rule out the carboxylic acid has two types of frequencies which will appear. One is for the carbonyl carboxyl group, another one for the hydroxy group. So we have to have a peak around, a broad peak around 3550 to 3200 per centimeter. So that is not given in the problem. So that means we can simply rule out A is not the one. And for the ketone, the value is between 1750 to 1680, which is much lower than the given value. So we can also rule out B based on IR values. And if it is a cyclic ketone, it should be 1720. That is also ruled out. So aldehyde appears at 1740 or 1760. So we can also rule out C also based on IR values alone, not based on chemical reactions. So we are left with option D only. So how the reaction actually proceeds? The reaction oxidizes only the carbonyl primary alcohol is oxidized to the corresponding aldehyde, and this aldehyde internally is attacking this the lone pair of electrons on the oxygen basically attacks this electrophilic carbon atom, which leads to the lactol formation. The lactol is further oxidized by PCC to the lactone, and the lactone generally appears at 1765 in the IR spectra. So based on that, we can say the given compound is option D. Thank you so much.